about O of n squared, if I want to say, let's say for example, O of n squared, right? I mean, in what sense does the red curve look like the blue curve? It seems preposterous. It's oscillating, and so it's a bit, look, you have to fall back to your definitions. So the definition is that f is O of g if f over g is bounded as n goes to infinity. And here, what you can do is you can say, let's say, g is equal to n squared. So for example, so you see that you have f over g is 1 plus sine, I'll just write s for sine. S is sine, c is cosine, okay? N squared plus cosine. But of course, sine is between minus 1 and 1, right? So I need to put an absolute value here, but it doesn't matter because 1 plus sine is always positive or non-negative, so I don't need to worry about the absolute value. And so this is 2n squared, and this is plus 1, which is, if you divide, you get 2 plus 1 over n squared. And 1 over n squared, if n is, let's say, bigger than 1, that's smaller than 1, so that's 3. So f is big O of g, which is big O of n squared. S, S, what's, sorry, what did I do? No, it's fine? Okay. Okay, so it's big O of n squared. So that's, even though it oscillates, and you can see it here, I'll plot for a longer range. And what we'll do is I'll compare it with 3n squared, and we should see that 3n squared is strictly bigger than the function. If I go from 0 to 100, yeah, it oscillates, but we can all agree that it's smaller than the 3n squared, so we're good. That's 3n squared is an upper bound. And then when you do the big O, you can ignore the 3. So if I go divided by n squared, so that I see what it looks like when I divide by n squared, instead of comparing this, we can see this is bounded. This is bounded. And that's what we want. So therefore, this f is big O of n squared. Now what's the leading term? There is no leading term. Because in order for it to be a leading term, it would have to be, so it would have to be some cn squared, right? Plus a lower order terms. But it just doesn't work because the thing in front of the n squared oscillates, so you don't know what constant to use in front of the n squared. You know what this light is? So you just don't know. So not possible. Because the constant, you see I've divided it by n squared here. So this is roughly speaking, this should be the constant that you would have in front of the n squared. And what is a constant? Well, it oscillates between 0 and 2, so it's not a constant. Right? Now, if I get rid of the 1 plus sign here, if I just get rid of the 1 plus sign, then we'll have a constant. It'll, oh, goodness gracious. So now we do have a constant. You see, now it looks like it's the principal term is n squared with a constant 1. And it makes sense. You see it n squared with a constant 1. And there is an oscillation, but the oscillation is much smaller than the n squared. So the principal term is n squared, and the constant is 1. With this case, with the other case, there's no principal term. This doesn't work. Okay? So that's the big O that we're going to be using. And like I said, if you have an algorithm that's big O of n squared, so big O of n squared, so let's say that you have so if you have let's say you have n, okay, and then let's say you have n flops, n squared flops, and cubed flops. So let's say that we have 1,000 here. is going to be 1,000 flops. This is going to be 1,000,000 flops. And this is going to be 1,000,000,000 flops. Now, let's try to think about how long it takes the computer to do these various flops. So I've already told you last time how fast the computer. Does anybody remember, roughly speaking, this computer right here, or the cell phone in your pocket? Roughly how many, within an order of magnitude, how many flops do these computers perform each second? Remember? 10 to the 12. No, that's too much. In one second, 10 to the 12, that would be pretty cool. So that would be what's that called? That would be called I believe that's a petaflop. So some supercomputers can do that, but not the ones in your pocket. Nobody remembers? 1 billion, 10 to the 9. Okay, it's easy. Billion. We all but billion, like I want $1 billion, right? You're not going to get $1 trillion. Forget that, right? $1 million is not enough, right? Clearly, right? It's a billion. It's 1 billion flops per second. Okay. So this is going to take 1 second. I forgot to put it in here. This is going to be 1 second. This is going to be 0.001 second, and this is the blink of an eye, right? This is so fast. This is 1 millionth of a second.
مرفق الكمبيوتر
Right. And when you do flop stuff,
هذا كله ما
billion is a good threshold. Somebody asks you, hey, hey Seb, I just hired you to program something for me. I want to know if it's possible to do, and they ask you to do something. You take your little chart like this and you calculate the flops before you start. If it's 1 billion flops or less, you say yes. If it's more than 1 billion flops, you say, well, now hold on a minute. This might not be possible. I mean, of course, if you can do 10 billion flops, it'll take 10 seconds, right? But we're not counting certain things. It might actually be that there's some slow things that are happening besides the flops. And then if you're in this situation, suddenly, instead of taking 1 second, it takes 1 minute or 1 hour, because it has to go fetch the data on the internet, or whatever it is. And the other thing that's going to happen is that if you're here, you can program it very badly, because it doesn't matter if you're very not a good programmer, and you're very wasteful and you do everything wrong. 1,000 flops, even if you do it completely wrong, and you somehow do a million flops instead of 1,000, nobody's going to care. It's going to be in the blink of an eye. But if you're here, you actually have to program to be a good programmer, because if you're wasteful with your computer time here, it's not
هذا
going to
ما
work.
هو
So
ترجمة.
it's good to know. 1 billion flops we can do it. Less than 1 billion we can do it. More than 1 billion flops,
حسابي ترى.
oh, we start to have to be careful now. Okay? It's useful. It tells you what's possible and what's not possible. It also tells you how to choose your hardware.
أنت
Am I going to
واحد
do it on
ما
this
لازم كيف
computer or am I
راسه.
going to try to run some time with
والله
this
لازم كيف
computer?
راسه.
Billion flops? Yeah, no problem. This one.
الله يستر
Billion
جوالك
flops,
لا يفهم.
like you suggested. Okay. Now we have to look at the
يعني فرنسا
supercomputer.
هذه يقعد فرنسا
هاتوك.
How many flops in matrix multiplication? Well, it says the answer right here. So, theorem,
ما أدري.
C equals AB. A is a P by Q matrix. B is a Q by R matrix. So C is P by R matrix. Flops equals 2PR times, no, PR times QQ minus 1. PR times 2Q minus 1. Which you can also write as 2PQR plus lower order terms.
وما بيشرحها قبل أخي نسي أخي.
So let's do a check. So if I go like 1, 2, 3, 4 times 5, 6, 7, 8, 9, 10. So that's 1 times 5 plus 2 times 8 1 times 6 plus 2 times 9, 1 times 7 plus 2 times 10, 3 times 5 plus 4 times 8, 3 times 6 plus 4 times 9, 3 times 7 plus 4 times 10. Now let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 flops. It's good to mark them. So if you mark the flops, it's here, 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 here. You can mark all the flops like this. It's good to do it. And if we do PR times 2Q minus 1, so let's see, what is this? This is 2 by 2, and this is 2 by 3, right? So P, Q, Q, R. So what is that? PR, 2 times 3, times 2Q minus 1. 2 times 2 minus 1, which is 6 times 3, which is 18. So you can see that it's the right formula. You can also try this. See what 2PQR is. 2PQR is 2 times 2 times 2 times 3. Which is, what is this? 6 fois 4, 24. 24. So you see that it's not quite right, right? So this is an approximation. Yeah? An approximation. The correct answer is 18, and the approximate answer is 24. But the approximate answer has the virtue that a 2PQR is a bit easier to process in your head than PR times 2Q minus 1 is more complicated. So it's just a question of how simple do you want it, and how accurate. And
مثلا ناقص الله
so how do we prove it?
الله
How do we prove it?
الله يزيلك
So we have CIK
مش أنا مغسول
is the sum from J equals 1 up to Q of A, I, J, B, J, K.
وجع عجل ناقص الله يزيلك
So then the question is, how long does it take
جسمي كله ثقيل
to compute one of these CIKs? So for one of these
أظن
CIK,
طالع له خلاص
we have to do CIK equals AI1 B1K
ما تجي النفس
plus AI2 B2K and so on plus
so
AI what is the middle? Q B Q K. Now, this is maybe I'm being a bit pedantic here, but I'm going to give myself an example so that I can see it. So I'm going to take an example with Q is equal to 3. So then this is AI1 B1K plus AI2 B2K plus AI3
أقسم بالله جسمي ثلج
B3K. So just so I can see it. Okay? And now I can count the flops. 1, 2, 3, 4, 5 flops. 5 flops. So what's a good approach for counting these flops? Well, we can see that there are products of numbers. There are 3 products, and there's also sums. There's an addition operation, but there's only 2 additions. So there's a difference between the times and the pluses. And this is called the fence post problem. So if you're putting up a fence and you have, let's say, you have 3 posts. So these are my posts. And then I put the fence in between the posts. Right? That's the fence. So if you have 3 posts, how many meters of, and you're going to put the posts 1 meter apart, right? You're going to put the posts 1 meter apart. How many meters of fence are you going to need? 2 meters, 1, 2 meters of fence. 2 meters of fence, 3 posts. So it's a fence post problem. There's 1 more posts than there are meters of fence, right? So here, what's the fences and what's the posts? The posts are the times. There's three products, so those are the posts. And the pluses, well, you can see that they're physically in between the posts, which are the times. So there's 1 less plus than there are times. So what happens is that if you do it more abstractly now on this guy, you're going to have up to q, right? So here I have q is equal to 3. I have 3 posts and 2 pieces of fence. Now I go up to q, so I'm going to have q posts and q minus 1 pieces of fence, right? So I'm going to have, so this thing, CIK, is sum of 1 to q of aij jk. So that's q products and q minus 1 additions. And so that's going to be 2q minus 1 flops. And that's for calculating one of these CIKs. But now I have to figure out how many of these CIKs I got to compute. There's not just one, right? That's one. CIK is 1 entry in the product. So if you look at my example that I did over here, this is C11, this is C12, this is C11, C12, C13, C21, C22, C23. So how many C's do I have here? We can count. 1, 2, 3, 4, 5, 6. I have 6 of those, right? So in this example, so let's call this example star. In star, there are 6 CIK. And each CIK takes how many flops? 5. 5 flops. No. 1, 2, 3. 3 flops. So 6 times 3 is 18 flops. So we see that to get the 18 flops, we have to see how many CIKs there are, how many flops is we need to do for each CIK, and you multiply them. So now in this matrix, C11 up to C1 PQR, so R, CP1, CPR. So this has P times R, PR entries. Each needs 2q minus 1 flops. So total flops is PR times 2q minus 1. And that's the end of the proof. So every year, I get questions about, oh, what do we need to put in the proof that we give you on the exam? I have two answers to this. If you're looking for the amount that will guarantee you the good marks, there's a law that we have in the department that whatever I did on the board, if you give me that, you get the full marks. So if you put all that stuff, you get the full marks. So that's one answer. And then I can also give you a bonus piece of information. That is, you can also get full marks if you don't have to do, because I did some examples in the middle of the proof, right? So if you didn't do the examples in the middle of the proof, but it was clear enough to me, then you would also get the full marks. So when I do the proof on the board, again, it's a law. If you do that proof on the exam, you get the full marks. But why am I doing the proof the way that I'm doing? Is it because everything that I'm doing is absolutely necessary? No, it's because I'm trying to be pedagogical and be friendly with my proof. Don't go too fast. Show each step in the most friendliest possible way. If your proof is correct, even though it's not as friendly as mine, then you will get the credit. With the caveat that sometimes people simplify too much, or I say simplify. Put yourself in my shoes. I get a copy. It vaguely resembles the proof that I have in the class, but it seems to be missing a lot of stuff. What's the difference between a student who memorized the first line and the last line of the proof, but doesn't actually understand what's happening, and a student who understands everything and only puts the first and last line because they think that's good enough? So that's the only caveat. So make sure if you've got plenty of detail. If you have this level of detail, you get full marks. If you choose to remove the examples that I do in the middle of the proof, yes, you will still get full marks without the examples. If you remove so much stuff that I can't tell anymore, then you will lose marks. Okay? That's how we're doing proofs.
علامتي اسم مريم مرحبا كده طافح
Gaussian elimination. Do we have any questions on the matrix product and the plots? No? Okay. Yes, in the back?
Can we see in a script, in an algorithm, like how to count floats in the algorithm?
You mean if you see an algorithm, is it possible to count the flops?
In a for loop, how many?
Yeah, you can stare at it and figure it out from the code. Absolutely, yes, you can do that. Yes, you're asking me to do it. What are you
I
saying?
think there's an algorithm.
Yes.
Yes. Can we see in the algorithm how many floats is in this algorithm?
Yes. So you can see that there's a flop here, and you can see that there's a flop there. Now this algorithm has a slight difference between what is there and what's in the analysis. And the slight difference is that here we have 2q minus 1. And in this algorithm, for simplicity, it's not going to be 2q minus 1, it's going to be 2q. So I'm doing an extra flop somewhere that's not needed. But if you very carefully read through this algorithm, there's one flop here, there's another flop there. This occurs q times, so now you've got q times 2. And then this occurs r times, so now you've got q times r times 2. And then this occurs p times, so you'll get 2pqr. So now you have your 2pqr, which is exactly what I said. The minus 1 is, in this theorem, doesn't correspond to this implementation. Now, fixing that so that there is absolutely a minus 1 is possible,
بس
but it makes the code slightly more complicated, and I have kept it as simple as possible, so I wasted a flop. I wasted a flop in this algorithm. Okay? But otherwise, it's almost the same.
قضوا هذه
Other questions?
مرحبا كده
Okay. Gaussian elimination. I'm not going to re-explain dot elimination because you should all know. Of course, you all know. You all know dot elimination, right? But I will do an example, a numerical example, just to get our feet wet. And because of ADHD, it will be ideal if I have pre-computed it in advance. Because me and computation
شكله حط درجاتك اليوم
makes my teacher.
ده امتحاني أنا
Well, she didn't know I was ADHD, but she was happy with that.
شكل محمد ثلاثة واحد من
So we want to solve ax equals b, and we've got a equals
مرحبا
3 minus 6,
مرحبا كده
1, 4, and b equals minus 12, 14. What's going to be the novelty in this section is not the dot elimination because everybody knows how to do it. I'm going to count flops. That's the new thing. That's what's important. So we're counting flops. I don't actually care about the numerical result. So what we do is we form what is it called, the augmented matrix?
شكل قال محمد ساقط كثيري خفصنا عليها شو قال له شنو قال محمد قال بس روحنا كلكم
And then we do a row 2 is row 2 minus, and I'm going to keep all the flops so that we can see them. So I'm not going to simplify anything prematurely. I will leave all the flops on the paper so we can count them easily. And this is very important because some of the places you're going to be, well, Seb, why isn't there a flop there? Well, that's why I'm writing all the flops that we're going to be doing. I'm going to carefully count them. Some of them are going to disappear. You're going to see some of, not all the flops
انت
you
متفاهم
might have
بالله
thought of are going to be present. So the top row stays the same.
انا
The
بكسك
second row is what I find very
كل ابوها
interesting.
شكل اشرب
So let me start here. So it's 4 minus a third. Now this, let's call this alpha. So we're going to compute this once. Or I think I called it L21. So L21
بالله خلص خلينا نروح
times minus 6. And here it's going to be 14 minus
الله ياخذ
L21
راسك ابو ضاف
times minus 12. What about this here? Am I going to do 1 minus L21 times 3? Am I going to do that? So you could do that. You could program it that way. You could do 1 minus L21 times 3. But that would be a bit silly. Because what are we doing with Gaussian elimination? Remember how it works. We put zeros below the
ما
diagonal.
عندنا خطه كيف
Why would we do
والله
a
خط
flop
احسن منه
if we already know there's a zero there? That would be wasteful. Right? So it's called optimization. If you know the result of a
الله
flop,
يزيدها
don't ask the computer to calculate it anyway. Just put the answer that you know. So this one, we know what the answer is. We put the zero, and it doesn't cost any flops to do it. Okay? And now here it's numeric, so I'm going to just put the numbers so that we have them. According to my notes, it's 0, 6, 18. I hope that my notes are generated by a computer program, but sometimes I can have a glitch in my computer program. And especially, I remember that I changed this one, so let me just see if we have the right answer. So it should be 4 minus a third of minus 6. So a third of minus 6 is minus 2, with double minuses and a plus. So we get a 6. And then here, 14 minus a third of minus 12, so it's 14
محمد
plus 4.
اليمين
So I wrote
اتطور والله طقع
And we can count the flops. So here's a flop. Right, flop. And what else do we have? We've got this here, this here, this here, and this here. So let me put some times. So how many flops do we have? 1, 2, 3, 4, 5. 5 flops. And that's it for the step that I call Gaussian elimination. And the next step is called backward substitution. So the Gaussian elimination itself is just reduction to upper triangular form. That's finished. How do we do the backward substitution? Well, we always do it ourselves by putting back the x's so that we don't get too confused. And I will do that for you. But realize that the computer doesn't manipulate x's. The computer works with just the numbers, right? So let's just put the numbers, the letters, 3x1 minus 6x2 is equal to minus 12. Right, that's how we always do it, right? 6x2 is equal to 18. We always do it like this, but there's a much more computer way of doing it that doesn't involve x's. Just mentally remove all the x's from here, right? And it's closer to what the computer would do. So from this one here, we go x2 is 18 over 6, which is 3. And then from that one, we have x1 is minus 12 plus 6x2 over 3, which should be 2, I believe. Is it 2? Yes, it's 2. Good, good. Okay, so not too many mistakes. And now let's count the flops here. So here I have 1 flop, and here I've got 1, 2, 3 flop. So that's 4 flops. And so the total is 5 plus 4 is equal to 9 flops. Yeah.
Can you go over why we don't need to count the flop for the 0 for optimization? Because
Well, I mean, that depends on how you write the program. So it's an indication right now of how I'm going to write the program. Because I know ahead of time but never mind the program. In real life, would you yourself do 1 minus 1/3 of 3? Would you do that? You wouldn't, right? Just because you know that it's a 0,
yeah.
right? So anything that you know in advance like this, as an optimization, you put it into the program. Now, you could not put it in the program, and when you're working in the lab, one of the labs has self-animation. I don't know if you'll do it this carefully, where you preemptively put the 0 without calculating this. I mean, it's a 0 that you shouldn't calculate. It's a 0 that you know. If that makes any sense. It's a 0 that you know in advance. You wouldn't calculate this 0. You know that it's there. You wouldn't do it. So why are you making the computer do it? That's my question.
How are you going to put it into the program?
You have to write the program carefully so that below where you know the zeros are, you don't do any flops. You just go. Let's say the matrix is called Z. You would do Z of 2, 1 equals 0. And there's no flops in the equation. You just write Z of 2, 1
ربي
equals
كاتب لنا
0.
كاتبه
And that's not a flop.
اعتراض عليه
Right?
Okay. And also, why do you count the 1 over 3 as a flop, but not the minus sign 3 on the R2?
So,
وفلوسي
sorry,
فلوسي
those are good questions. Um,
Is it because you're counting them inside the matrix?
So yeah, we have to be careful. This is a vector operation here. This R2 minus, it's a row operation. Be careful not to confuse, even though there's exact same
قلت له
symbols
اسمه
for the
محمد.
vector and row and scalar operations, these aren't the same, okay? And this operation here, I didn't count it because I counted it here. So you shouldn't double count it. Yes?
Yeah.
كتب إسلام محمد دوسي رد مديان ولا إسلام محمد بس تأكيد
in the matrix.
في
This one?
موفي واحد منها واحد طاح.
I didn't do whatever counting it when you go up there.
I didn't count the time here. This operation here, I didn't count it. You see there's no little arrow on it. I didn't count this. Yeah, I just
والله ما
counted the
كان
division.
ثلاثة أموت.
Okay, here I'm just counting the
شو
division.
لها أروح معك؟
I'm not counting that and I'm not counting that. Okay? Now if you want, you can count those, but you have to be very, very smart and sophisticated. What I did to count those is I did this. That's what I'm doing here. I'm counting those. I'm counting that and counting that here. Right? Very, very carefully. That's what I'm doing. So anytime you have a vector operation, you have to extend it to see what it's like.
درجاتك أعطاني.
It's unfortunate. In the mathematical notation, we don't distinguish between scalar operations and vector operations. And to count the flops, what you have to count is scalar operations. And vector operations convert into scalar operations. To convert them into scalar operations, you have to do this. That's what I'm doing here. Yeah? Does that make sense? That's basically the whole problem, is to convert everything into scalar operations so we can count them.
ما العصا.
So I can't count them here, they're vector operations. If I count them here and then I count them here again, I'm double counting them. Okay, any more? No? Don't have my glasses, so you have to signal pretty strongly for me to see you. If you have a question. Okay, so this is the 2x2 case. You know, I know it looks pedantic. I'm doing a 2x2 Gaussian animation. You all know this before. But it's useful. I mean, count the flops. You didn't do that before. You had questions. I think it's a worthwhile example. But now let's do a proof where it's n by n. Okay? If I jump right into the n by n, oh, it's very confusing. So the theorem is
الله
A
يقعد معي نفس.
is n by n,
الله يبارك
and B
فيك
is a
سلمك.
vector,
اشرح لنا أنت.
then
ما أخش تعال.
Gaussian elimination is 2/3 n cubed plus lower order terms flops. And backward substitution is n squared. It's exactly n squared flops. Exact. So Gaussian elimination plus backward substitution altogether is 2/3 n cubed plus lower order terms flops. And now people are thinking, but Seb, 2/3 n cubed, that's Gaussian elimination. Well, backward substitution is n squared. Why do you say that together it only takes 2/3 n cubed? Where did the n squared go? Ah, I'm glad you asked. It's a lower order term.
واحد
N
وخليه.
cubed is the principal term. The backward substitution takes a trivial amount of time compared to the Gaussian elimination. Let's do an example. N equals 2. That's what we just did. 2/3 n cubed plus LOT is 2 cubed is 8, so it's 16/3 plus LOT, which is 5 1/3, right? So it's 5.3 repeating plus LOT. And that's approximately equal to, how many flops did we count? Counted 5 flops. And with the exact example, we did 5 flops. That's pretty good, right? That's a good approximation, the number of flops. And backward substitution, so this is Gaussian animation. Backward substitution is exactly n squared flops. So that's 4 flops is exact. Is exact. We did that calculation, we got it exactly. So that's exact. And the other one has a little bit of a approximation to it, 5.3 repeating. When you read the proof, you'll see why I have an approximation. It's because I want to save some time and avoid to calculate something that's very hard to calculate. But in fact, it is possible to get an exact number here. And if you want to show off to your friends how clever you are, you can take my proof and get the exact answer. Instead of saying 2/3 n cubed, you can get a proof. So you
Yeah,
can
but see.
use a polynomial in it. If you
تكفى.
want, but I'm not going to do that.
قول
It's
خلاص.
too tedious. It's too tedious. I mean, I don't want to belittle it. I think it's nice to be able to do it. It's kind of a trick. But this is good enough for us, 2/3 n cubed. Hold on a second. Let's scroll. Oh. Right. Okay. Well, to be frank, I think I don't want to launch into a proof that's 1604. Now, before I let you go and you start making a ruckus, let me just, I had something I wanted to tell you. Let me remember what it is. Did I say that there's no test in week 5? Did I say that?
Yeah.
Oh, good. Whew. No, we're all happy, right? This is great. Great news, right? Okay, so just a project in week 10 here. You guys are free.